machine learning and deep learning applications. By now, you have like gone through how to prepare your environment, which modules to load for Python, for various other work. Maybe it's just for visualizations. Maybe it's just for pure doing some GPU coding for parallel software, or um, learning how to work with pandas and other stuff. And now this is we are going to look at like major three applications or libraries. The popular ones, of course, for machine learning and deep learning, which is the scikit-learn, PyTorch, and TensorFlow. And we'll look at some examples after the break, and most importantly, I think we'll look at some like do's and don'ts and how to work with HPC environment in general if you're working for machine learning or deep learning applications. So my attention will be most on that one and not actually on teaching you these library itself, which I believe there's plenty of resources for these libraries and they'll do a much better job than this just 1 hour session. But here I'll try to like show you or tell you like what are like the do's and don'ts when it comes to running these applications for your work on your HPC cluster. So these three applications, scikit-learn, PyTorch, TensorFlow. I'm not sure if you have used scikit-learn by itself, but this is a popular one. This is for traditional machine learning application. And this was like built top on your NumPy and SciPy. SciPy being another very popular library for if you have like computational scientific computing related stuff, like series like Fourier transforms, even regression, for example, and other scientific computing related work. Scikit-learn is I think was one of the first ones to enter into like machine learning, how to build using these libraries to build machine learning applications. And it has a very good community and a very extensive documentation for itself. And there are other libraries which are now built on top on scikit-learn. Whereas PyTorch and TensorFlow are majorly for deep learning work. And my favorite being PyTorch now. I've worked with TensorFlow, but I've seen like over the years, TensorFlow's popularity has reduced and its community support has also reduced. And you might see this also in very much in our HPC clusters where we do not have very active support for TensorFlow, be it for monitoring purposes, building applications, or whatever. This has also been impacted because with the TensorFlow 2.0, there was like a lot of changes from the previous version, and that broke a lot of applications. And many vendors like Intel started building their own or maintaining their own TensorFlow versions. So TensorFlow in itself branched out, and they stopped giving support directly. Like the Google stopped giving support directly for certain vendors. So yeah, sort of on the mercy of these vendors to give, maintain these libraries. And if it's not maintained by community, it's very difficult for the vendor to know what the community wants, right? Whereas PyTorch was from like beginning itself by Meta was made keeping in mind that this will be made for like researchers and it should be like easy to work with. So when you look at the PyTorch code, it's very intuitive to work with. Whereas TensorFlow, there are multiple like wrappers over wrappers, and it gets confusing sometimes. At least for me, it did. Nevertheless, people are using both TensorFlow and PyTorch. If you're into like IoT devices, I think TensorFlow is still very popular for federated machine learning stuff also. Whereas PyTorch is like one of the best de facto one to go for if you're working with any deep learning application, reinforcement learning as well as building LLMs, for example. In various HPCs, we have sort of have these applications. If you are from C3SC, then well, Alvis is meant to work for all the AI applications, as it's very well maintained for these. There are both TensorFlow and PyTorch. And then there are also data sets and models already downloaded for you to work for, like if you would just want to test out your machine learning, deep learning stuff, or just play around with it. You can check their documentation. UPPMAX, we have Pele now. Previously, we had Snowy and Rakam. There we had a sort of good support for machine learning and deep learning stuff, but with Pele, which is quite new, we're still building these modules. And for example, TensorFlow is still not there. PyTorch is there, but it's only for CPU only PyTorch. If you're from Bianca, I don't think so anyone is, but there is one package which includes everything, but it's old Python. And HPC2N and LUNARC both have TensorFlow and PyTorch, with both of them having like CUDA versions of these. So I think you're good to go if you just want to do like bare minimum with your TensorFlow and PyTorch, because they also work with GPUs here. Yeah, this one as well as this one. NSCs, well, it's not much. Actually, they don't have TensorFlow and PyTorch. You have to build your own environment. And yeah, I think you just have to work with that. You cannot do quick testing if you want to. And PDC, they have Singularity containers now called as Aptainer. And you can load these containers and use TensorFlow and PyTorch. I don't think we covered any Singularity or Aptainer related stuff in this whole workshop, but I would encourage you to actually get comfortable with Aptainers or Singularity to build your own environment for machine learning, deep learning, because sometimes these applications can be quite complex and there can be like many dependencies. Having Aptainer run everything in a container, I think solves a lot of issues sometimes. But we are not covering how to build any containers like that. But you can look at your HPC's guide documentation to know how to do it on that. More or less is the same for everyone. I have given some resources to look at, some examples that you can look at if you want to start anywhere. And for advanced users, there's some parallelization techniques to look at for all these three libraries. We are not covering how to run parallel code with these libraries. Nevertheless, researchers do, of course, do parallelization with these libraries. This is currently out of the scope for this session. And also for hyperparameter tuning your models, there is some guideline, but that requires some, for example, Ray cluster, which is not supported by many HPCs. If you're from Alves, maybe you'll find Horovod library there that you can either install yourself or use in the module and then do parallelization, hyperparameter tuning using that kind of library. All right. Any questions up until now? Maybe I didn't check. I should probably, it's nothing on the chat. And I always get confused with Zoom. To look at the, oh, well, just unmute yourself and ask me a question if you have any. I'll assume you do not have any yet. Okay. Ah, there it is. Yeah, no questions yet. Okay. All right. So these are some common libraries or tools for Python that we see people use. And I've just given the modules that you can load for various clusters here. And this is just for like starting bundles. For example, you want to just test it out whether your code is like bare minimum working on certain library. I would not recommend this to like be your, for like so-called production way of deploying your application or working with it. Create your environment, put your environment, freeze your environment, and use that for your experiments for a longer run. But for the starters, you can, of course, module load these and play with them. So a lot of them are common. For example, if you look at like Pele, Kamikaze, and Alvis, um, many of these are having the same and nomenclature naming. So these are built on easy build and you can find them readily available. I've given PyTorch here for Pele, but just to remind you that this is only CPU for CPU, whereas the one on Kamikaze is GPU available as well. Same for the Cosmos as well. They have almost all the libraries available there. I added Keras here, but I don't think anyone would be using Keras explicitly. TensorFlow has a backend of Keras and now, so Keras is like a backend for TensorFlow. And standalone Keras, I don't think it's anyone uses now. I'm not sure unless you're maybe developing something specifically for it. Let's see, and Beautiful Soup is quite common if you're using, you need to parse documents and download documents from the internet. And Beautiful Soup allows you to like parse these properly. You can select sometimes the elements of particular pages as well, or classes, and just parse those part. So if you are into like natural language, NLP related work and you want to download things and clean the data, then this might be handy. Seaborn, I think you've already seen Matplotlib as well. For Dardal users, again, this is most of this is into containers. So TensorFlow, Keras, PyTorch, these are all into the containers. You have to load the container. And I don't think, yes, sklearn is available there. Alvis has everything because, of course, it's meant for AI related work. So starting with, this was just the overview of various modules that you can load on different clusters and what is available there. Of course, there's more available to it. Depends on what exactly you want. These are the most common ones that people, researchers use. So scikit-learn, I was already talking about it in the beginning. It's based upon SciPy at NumPy, and for visualizations, they use Matplotlib. You might also see that it's more CPU heavy than GPU heavy, by the way. So if you're using scikit-learn, and you might be using more cores than GPUs, depending on your work, but mostly it's more CPUs than GPUs. Here is a table of common building blocks for any scikit-learn related application or model. And you might find this also, like this nomenclature also passed down to other newer libraries. And I think sometimes it's easier to relate with when you're working with the newer libraries. So the most basic one, the common one, comes with the estimators. The estimators are these the class which helps like identify which hyperparameters are needed, what's the value for them for that particular data distribution that you have. And they implement this with the dot fit method. And that's how your like model trains. So you do a model dot fit, giving your training data set, and it depending on what model it is. For example, linear regression, nearest neighbor, KNN, decision tree. It will understand the data distribution and find the best hyperparameters for it, parameters for it. The one which accompanies estimators is transformers. And this transformer is different from your language model transformers, by the way. There might be a slight confusion there. But transformers basically means once you have learned these parameters, you can apply them over your, let's say, test data set and transform your data set data into the prediction values. So you can use them. And they also give you like dimensionality reduction, PCA. This will be also covered again in the next session by Anders. Or if you are into like classic NLP related work, then DFIDF vectorizer, which is this term frequency, inverse document frequency for your documents. And this is the standard scaling of your values. Given all these like many models and transformers that you can have, there's a neat way to stack them together using pipelines. And then you can, this pipeline again, you'll find this wording again if you're using, for example, Hugging Face transformers library. They use also these terminologies, right? So pipelines might also be there, used there. Or if you're using another NLP related library from Explosion, for example, Spacey, they also use these terms. So you can stack these estimators and transformers, and it will be done like step by step, like so, like in a list. Data sets is just their way to like give all the classic data sets like iris data sets to you. So you want to test it out or just play with it. The digits, handwritten digits, and housing pricing data sets like these. And similarly, if you're using Hugging Face, you again find data sets library there from transformers that lets you download data sets. That's a different kind of data sets. I mean, those are very heavy, big data sets, and they usually shard those data sets in a proper format. I don't think data sets from this more like scikit-learn is doing all that kind of like latest techniques to shard your data sets. Finally, you have to, after building a model, you have to do evaluation. So there are model evaluators for it. Depending on what kind of matrix you want to optimize for, you want to maybe do cross-validation for your clustering model, regression model, whatever model you build. So you can use these evaluators. For example, mean square error is quite a common one. Just simple accuracy score is another one. So you have your model, you fit your model on this training set. You do some predictions with this model, and you use this estimator on these predicted value as well as the test data set to calculate the accuracy, for example. Finally, parameter searches. These are quite handy if you're doing after building a model. Of course, you will have to like fine tune your model where you would need proper hyperparameter tuning. So you can do like you can give an array or a list of all these hyperparameters for that particular model. And common ones include like grid search, where you get just a list of them, or random search, or it just searches randomly. But there are other advanced techniques like Gaussian search as well, where it understands the data distribution and then finds those parameters which are closer to the, like say, global minima, let's say, for example, for which let's say you have a loss function you're trying to minimize, for that particular one, and for your data distribution, what's the best hyperparameters in that case, if your data distribution is following certain Gaussian distribution. These are very basic examples that I've given for linear regression, for searching k nearest neighbor, and for a simple decision tree. There's nothing special going on here. Just using these previously discussed methods. You can see like you can use this model equals, let's say, linear regression. You fit on the data set that you have. This is a dummy data set. You make some predictions. As simple as that. Same here. In this case, we are using train test split function also. This lets you like give a percentage for which you need to split your data set into. Let's say in your training is 70%, testing is 30%. And to make it more reproducible, you can also give like a seed, in this case 42, let's say. So you get all your data set splits, and you again do a fit onto whatever model you're doing, k nearest neighbor in this case for 3 neighbors, and you get your score. You can use your evaluator there. Similarly, decision tree, same stuff. Okay. I'll be jumping over the exercise right now. We'll come back later after break. PyTorch and TensorFlow. First of all, if there is any, again, question, just ask me in between. PyTorch and TensorFlow. Now we are on to deep learning stuff. I think it's, as I can like compare both of these, you can clearly see I've tried to like, this is not a proper working code. This is a dummy example, but you can clearly see like there's a, TensorFlow has like a little bit of bloated code. Whereas PyTorch is quite self-explanatory. For example, if you have a variable, you can create like tensors. Like tensors here and variable TF variables are comparable. These are like special data types for storing data, multidimensional data. And you can do a backward pass on your, calculate gradients on a particular function. This is a very simple and stupid function, just summing your data. Whereas in TensorFlow, you'll see something like this going on. So if you have to like create a neural net, and it's a very simple neural net with 2 inputs, 2 outputs, you create a layer and you have your inputs, which are like just 2 inputs. You give that into the layer and you get the output. And similarly here, you can see something similar going on with just a little bit more parameters here, but more or less is the same. And you can see like TensorFlow is using Keras underneath it to create a dense layer, which is a simple neural net layer. And something like optimization using stochastic gradient descent algorithm, SGD algorithm. So there is an optim.sgd for that. Similar to that is keras.optimizes SGD. And you have your, let's say, objective function or a loss function that you want to minimize for. So for example, square of the inputs and summation of them. So you can differentiate them. You can calculate the gradients. And here dot backward does that, and dot step actually applies those newly calculated weights, like those delta of those weights to the previous weights. Whereas TensorFlow does something like this. You have to call green in tape, input in the layer, and similarly do this summation over the square of the values. And then calculate the gradients and apply those gradients like so. There are 2 examples here that you can test out in this next after the break session. This is this is the part where we talk about like, okay, is there any question? Again, just ask me in between. Now, this is the part where we talk about what to like remember while you are building your machine learning, deep learning code. Excuse me. Now, these are like some tips and tricks that I learned while helping some researchers or doing my own projects or um, seeing what, for example, there are courses for machine learning, deep learning on HPC clusters. Sometimes, what are the teachers teaching to their students, the master students, for example, or PhD students? And in general, these apply for like also on your, if you're, let's say, working on your own personal laptop also, and you're not using an HPC cluster, you can also apply these techniques. But specifically for like distributed, your distributed file system, where also you have a compute node, a login node, and these are also distributed. You have to pay attention to a lot of small things in between. Otherwise, not just you'll be wasting your resources, but you'll also be wasting your own time by understanding, okay, why is my, let's say, code giving me an out of memory error, or why is my suddenly I'm not able to create new files into my file system anymore. Because many of these libraries just leisurely take up all the space and all the VRAM and the CPU cores that you have on your system. So you have to like really constrain them sometimes to tell them, okay, this is what my, let's say, cluster looks like, my file system looks like, and just work with that. So starting from like collecting your data, and before you start building your model, you have to like understand your data set. Um, you'll be working with GPUs, many cases, and these GPUs have different capabilities. So let's say if you're working with T4, which is like the basic one, and many HPCs, you will notice that you cannot even run models which are like having data type as BF16, which is brain float 16. It's a special form of somewhere in between FP16, FP32, commonly used for deep learning applications, but you cannot run it on your T4 now. You can actually, but internally, for example, PyTorch will convert BF16 to FP32, and you might think that your model could have fitted onto the GPU, but it's not, because, well, the data type has been converted, auto-casted into a FP32 now. Uh, Also, GPUs have different tensor operations for different data types. So you can look at the, let's say, A100 versus A40 or L40S and see which of the data types is it having the most tensor operations for. What is the, like, they do benchmarking and they tell, okay, this is faster operations on FP16 versus for FP32. So pay attention to that, because that will dictate whether you can even fit your models on it or data set along with the models on it. Like if you're coming from Pandas background and you have been using it, it's also appropriate to also look at those data frames sometimes. And you can change the column data types for each particular column to make it reduce memory footprint by a lot more. Um, a common mistake that people also make is when they start developing, they just pip install things. I'm talking about version management now. And they just keep developing their stuff. But I've seen that with machine learning, deep learning applications and libraries, they are evolving so fast that by the time you are like in the next month, they have already introduced, deprecated or given a warning for the previous functions and introduce a newer one. And suddenly your application is not working for our systems. So please do like freeze your dependencies. So if you have like requirements.txt file where you have your Python libraries, so you can give like, for example, I know torch equals 2.4 point something. So that freezes torch for your work, right? So do that for like make a common practice to freeze your work while you're developing your code. Um, this is very obvious. You have to version manage your code. So starting a Git repository is easier to work with. Just to make sure that when you're doing that, sometimes there can be use cases where you are doing hundreds of commits over multiple data. I don't know if you're working with a genome, for example, and there are many files for a data set. And I mean, let's say you are doing some very small changes to many files together, then Git can be very slow in committing on a distributed file system. So maybe then version management might software like Git might not be very helpful. That might actually slow you down. So it depends on your use case. Um, Another common mistake that we see here is people just conda install, conda activate, and pip install everything. Maybe download models from Hugging Face, and they do not remember that everything is going into your home directory, and home directories everywhere is very small in number of file sizes, total size, volume, as well as number of files. So redirect them, use environment variables that those libraries provide to redirect them to different folders. Um, One benefit of having, of course, everything in home directory is like usually this is not for all the HPCs, but having more IOPS. So in that case, maybe that makes sense to keep your stuff into the home directory. Start always like small with your models. If you have like a large data set, of course, this is obvious again, but I've seen students make this mistake that they start with a big batch size, even if it fits on the GPU and everything, and then it takes very long time for even to it to converge and give results. Meanwhile, they have to run like long jobs and wait for it. So it's very inconvenient for them to like work with long running jobs. And then in the end, it doesn't make even sense that, it didn't even work. So start with very small batch size. Start with sequence length is for NLP related work. If you have a language model, large language model, for example, then small sequence length as well. This will also fit in small GPUs then. Then you can slowly scale it up once you have tested small benchmarks onto a smaller batch size. It will, of course, reduce your debugging time as well, give you shorter training cycles, and also prevent out of memory errors, which is quite common for GPUs. And if you have a big batch size along with a big model, of course, it won't fit into the GPU. Maybe the first part is loading the model onto the GPU. That might work, but then it starts getting the data set and loading that, and that doesn't work because the batch size was very big. Be careful of the input-output operations for your work. Maybe it's not the first thing you look at, because the first thing maybe you look at the total volume of your data set as well as the model you're using. But some cases are, as I was saying, there are many files and checkpoints than just a big data set and a model. For example, if you're creating frequent checkpoints of your models, you're training it and it saves after, let's say, every 10 steps, because you want to be really make sure that you're creating your graphs, training graphs, for example, very nice and accurate. But this is also adding on to like many read and write cycles onto your drive. So this might slow down your training itself. But on the contrary, also large but few files may also slow down your data loading. So you have to like balance it out. Maybe it's too small or maybe it's too large. With machine learning applications as well as deep learning, this has been talked about in the previous session with big data with Python. So look at what kind of data set is the best for your use case, because sometimes with deep learning applications, there are many data types, for example, HDF5, but now Paraquet or .arrow, these are also quite common to see. And these are very well like sharded uh, with good metadata data sets. So your application knows how to quickly fetch and index them properly. And it becomes easier for the application to read your data set. So find the best suitable format for your data set. And just don't forget that, when you're working with your HPC, you have a compute node. You have your login node, compute node, and the compute node also has its scratch or temporary folder, which is on the node itself. And this is the one which is like quickly accessible to your running program. So make use of that if you think you actually can redirect some of your data to that temporary node for your temporary files, because it will be quicker then. A little bit more about storage management. So keep monitoring your like quotas for your project, because it just quickly bloats up when you're doing checkpointing and reading data sets quickly. Many libraries on the fly also download small runnables or libraries and even small data sets when they're running. So we never know how quickly they will bloat up. Also, when you're like running from your personal VS Code onto a particular login or compute node, the VS Code itself will have many of its small files that it will create in between. Compressing your data set is another technique where you feel like if you already know your data set work is done, you just zip it up and keep it. I think this should have been the first point, which is to set your, for example, HF home, if you're using, for example, Hugging Face or Conda packages directory outside your home directory. A little bit I was talking about here as well. This is just to like reiterate over the fact that these gets very filled very quickly, and suddenly in between your work, you cannot run your application at all. So it's once you start setting your whole HPC environment, just start with setting up these environments first. Whatever library you're using, just Google that library along with like environment variables, and you should find some documentation about what are the common environment variables that these libraries produce and use. So make sure that you're pointing it to your personal, for example, project folder, so that you do not use all the home directory. And finally, like clean up your temporary files, pip, for example, cache purge or conda clean all. So you can quickly clean up all these small files very quickly and make up more space when you're working with your application. Then we have like GPU memory management. And this is mostly when you're like doing some heavy inferencing with your models or training or fine-tuning your models. Of course, like common ones are HTOP and NVIDIA SMI, and HTOP for your CPU work and NVIDIA SMI for your GPU work. So you can see how much memory is being consumed. If you're using PyTorch, this is a very interesting PyTorch thing. It's a function. You'll have to Google this, but the PyTorch provides a function to save like the memory footprint on how much memory each step used. And it creates a pickle file, and that pickle file, you can save it as a file. And after your work is done, you can upload it to this particular website, Memory Viz. It gives a very good breakdown of how PyTorch has utilized its memory, the GPU memory, which is quite handy if you're specifically doing like model fine tuning or sometimes also inferencing. You can actually see which section of the GPU memory was consumed by which step of your application. NVIDIA Insight is another one, which is, well, I think it's available on Alvis, but not otherwise. TensorBoard is another profiler which is used for monitoring your work. We had this in UPPMAX earlier, but not on Pele anymore. But this is available on Alvis, for example, if you're on Alvis. Again, use small batches to avoid OOM errors. Use gradient accumulation for training. This is a technique for using, if you're using PyTorch again, then you can specify it to like accumulate the gradients before it applies those weight updates to your neural network. But at the same time, you have to like remember that, let's say your total batch size is 4, and then you say gradient accumulation is at every second step, then effective batch size increases because it's not letting the model get updated. So effective batch size increases 4 times 2, 8. And then because of that reason, well, you save certain memory. But at the same time, there are some trade-offs as well. So you have to see how quickly your model is getting trained because of this reason. As it might get slower to train with, but at least you will be able to save a little bit of memory. Then there is another concept of mixed precision training. If you're again on Alvis, there is a documentation a little bit on how to do mixed precision training. So PyTorch and TensorFlow both provides these methods which can change the data type of your certain parameters on the fly, so that it, for example, knows that not every parameter needs to be in FP32. Some of them can just be in FP16, and that will also work. And this reduces memory footprint by a lot. So be aware of mixed precision trainings now. This is getting common day by day. Lastly, like with LLM, if you want to use LLMs in your work for inferencing and training or fine-tuning, then there are some VRAM considerations you can make. So in inference time, you can quickly calculate how much VRAM your model might take by understanding how many parameters it is. It's usually like n parameters. You can check this on Hugging Face model card, multiplied by how many bytes each parameter is for. So this is a quite common one, which you'll do. Let's say it's a 3 billion parameter model with 16 brain floats, BF. Then 4 4s are 16, so 4 times 4 3s are 12. So 12, almost 12 GB would be required for a 3 billion one. But also multiply that by like a little bit of overhead factor sometimes, just to make that little bit of gap. Sometimes you need to load your data set, as well as the PyTorch library is also very big when it gets loaded onto the GPU memory. So keep a 1.5 times factor there. Same with the training. It depends on what kind of training, or so I should call this fine tuning, by the way, not training. Training would require like many GPUs. Whatever the LLM inference VRAM cost was, multiply that by more 2.5 or 3.5. Even more, so that the fine tuning might take even more time. But if you like, it's a full fine tuning, it's a lot of VRAM requirement. If it's like a more parameter optimized fine tuning, like LoRa, QLoRa, these techniques, where they're very conscious about what parameters they're updating the weights for, then maybe it's even lower. Lastly, these two, job monitoring and performance optimization. Keep in mind, like you have to also babysit your models while they're training. If let's say you are on a compute node interactively, then start it with like a tmux session and make it a habit of tmuxing, because you can connect and disconnect the session even if you have if you have to like move out from the compute node session, you can again connect it later. So tmuxing is helpful in that case. Log everything, like your checkpoint everything, your steps. There are neat libraries to do all these kind of logging and checkpointing, timestamping. There's like weights and biases. There's this one. Then there is another one called, it's a bit slower, but there's another one called track IO. I'll just close this. Track IO. This is another one, tracking lightweight experiment tracking libraries. These are very popular to track your training curves. And performance optimization is highly variable on what kind of work you're doing. With PyTorch, there is something called as torch.compile, which will pre-compute the graph, which is it's trying to like optimize for. Also, sometimes it depends on what GPUs you're using. So if you like, for example, using Hugging Face, I know that they have Transformers library. You can just Google Transformers GPU. They have a guide for this, what to look at, how to optimize for GPU. But otherwise, you can also log your NVIDIA SMI into your just a simple text file, and that will also give you an idea of how much GPU was being utilized, right? And I think that's pretty much it with this part, and we are 6 minutes short. We have a couple of like 4 or 5 examples to look at. And I've given some miscellaneous examples as well. These are simple examples for PyTorch and TensorFlow by creating your own environment. And these are available if you have already, let's see, if you have pulled the repository, you will find it under exercises folder day 4 MLDL. These are the Python and IPyNB files, and the data set for TensorFlow and PyTorch are in their respective folders. So before we go into the break, I would ask if you have any questions related to anything.